So, hello students. Now let's start doing some constitutive modeling, and one of the simplest constitutive model that we can think of is a bilinear elastic model, and let us see how we can do some computations by using this bilinear elastic model. And the basis for this is our decomposition of the stress tensor. In one of our previous classes, we had seen that the total stress tensor can be decomposed into some spherical stress tensor P, and then the deviatoric stress tensor S. The P is our hydrostatic pressure state that does not cause any failure because it is compression from all the directions, and the soil is extremely strong in compression. In fact, in pure compression it will not fail, and then the failure is only because of our shear stress, and then we can actually control our parameters. See, there are different modulus terms like the bulk modulus that controls the volumetric strains, and then the spherical stress tensor, and then the shear stresses are controlled by the shear modulus. The shear stress is the G times gamma, where gamma is our shear strain, and by playing with these numbers we can approximately simulate our strength of the material and so on. And so this is how we decomposed our total stress tensor into a hydrostatic stress tensor or the spherical stress tensor, and then the deviatoric stress tensor Sxx, Sxy, Xz and so on. And our constitutive equations we have seen in terms of the Young's modulus and Poisson's ratio. We can think of the same constitutive equation in terms of other parameters, the bulk modulus and shear modulus, the bulk modulus and Young's modulus and so on, so that we can actually get more flexibility. And when it comes to the soils, the simplest strength equation can be obtained by using the Mohr-Coulomb strength theory, where we can say that our tau max is C plus sigma and tan phi. That is an equation to apply on a particular failure plane, but in more general sense we cannot apply that C plus sigma and tan phi. We can only apply it in terms of our principal stresses sigma 1 and sigma 3, and our Mohr-Coulomb yield surface in the tau sigma and plane. On the x axis we have the shear stress, the normal stress sigma, and then on the y axis we have the shear stress tau, and in this space this is our shear surface or the yield surface. The intercept on the y axis is your cohesion, the cohesive strength, and the slope of this line is the friction angle phi. And if you draw any Mohr circle based on the stress state that you have, if the Mohr circle is within the yield surface, we say that the stress is in the elastic state, and if it is just tangent to the yield surface, we say that it is at the limit state. And any Mohr circle that is cutting across the yield surface is not admissible, it is not possible. Then we have to do something whenever that happens, and from this Mohr circle that is just tangent to the yield surface, we can by looking at this triangle OPQ, we can derive a relation between the sigma 1 and sigma 3 in terms of the C and phi. The sigma 1 is the maximum principal stress, sigma 3 is the minor principal stress, and sin phi is PQ by OQ. PQ is the opposite and OQ is the diagonal. OQ is this C times cotangent phi, this small length up to the y axis, and then this length, that is the mean normal stress, sigma 1 plus sigma 3 by 2. And sin phi is PQ by OQ, and by simplifying this equation we can write the sigma 1f, that is the maximum principal stress sigma 1 is 1 plus sin phi by 1 minus sin phi times sigma 3 plus 2c cosine phi by 1 minus sin phi, that is equal to Kp. This 1 plus sin phi by 1 minus sin phi is our passive pressure coefficient Kp, and this term cosine phi by 1 minus sin phi is a square root of Kp, and we can define a yield function or yield surface f in terms of this by slightly reformulating this like this: sigma 1 minus sigma 3 minus of sigma 1 plus sigma 3 sin phi minus 2c cosine phi. Actually, this type of drawing the Mohr circle, we can do it on a graph sheet, but we cannot implement this in a computer program, and we need some other method for seeing whether we are in the elastic state or the plastic state, and for that this type of equations they help us. So, if your f is less than 0, the soil is in the elastic state, and f is 0 and the soil is in the plastic state or the limit state, and f greater than 0 is not admissible. We cannot accept any stress state that is crossing the yield surface. And based on these observations, we can develop one model called as bilinear elastic model in terms of the bulk modulus K and the shear modulus G. And the K is the bulk modulus that relates the bulk stresses or the volumetric stresses and then the volumetric strains, and that is K is E by 3 times 1 minus 2 mu, and we can also write it as the mean normal stress divided by the corresponding epsilon V. GT is the tangent shear modulus. It relates the shear strain and the shear stresses, and the GT is related to Young's modulus and Poisson's ratio as E by 2 times 1 plus mu. And if we formulate our constitutive matrix in terms of K and G, we can calculate our tangent Poisson's ratio mu in terms of the K and G as mu is 3K minus 2G by 6K plus 2G, and the subscript T for the shear modulus is to say that our shear modulus will change during the analysis, and our constitutive matrix in terms of the K and G is written like this. The here the stress multiplied stress is equal to constitutive matrix multiplied by strain vector, and if you look at this, so at the limit state, as the shear modulus tends to 0, our Poisson's ratio will tend to 0.5, right, and our shear modulus G we can control based on whether our Mohr circle is in the elastic state or at the limit state. Okay. And our bulk modulus we can keep it as constant because there is not going to be any failure because of the spherical stresses, and the shear modulus G is set to some initial value when our yield function is less than 0, and when the yield function is greater than or equal to 0, we set the G to a small value GT, very close to 0 but not 0, so that any further increase in the shear stresses will not happen. So, beyond that plastic limit, even if you increase the shear strains, the shear stresses will remain more or less constant. And at this state, our Poisson's ratio tends towards 0.5, and our this is what we have seen earlier. And if you plot a graph between the J1 and epsilon v, it is a straight line, that is the k, and then the tau versus gamma is initially the shear modulus is Gi up to some limit when your yield function becomes 0 or greater than 0, and beyond that the G is set to some small value Gt. It could be 1% of the initial value or 0.1% and so on, like that we can decide based on the problem that we have. Okay. And there is another method of forming the constitutive matrix in terms of bulk modulus and then the Young's modulus. Instead of the shear modulus, we can directly formulate in terms of the Young's modulus, and this is the equation, the constitutive matrix in terms of our bulk modulus and then the Young's modulus, and then the tangent Poisson's ratio is 1/2 of 1 minus E by 3k, and at the yield limit our E could be very small, and so at that stage our Poisson's ratio will tend towards 0.5. Okay. So, let us look at our KG type model, the bilinear elastic model. Initially our G, the shear modulus is set to some finite value, and then once the yield function becomes positive, that means that our Mohr circle is just crossing the yield surface. We set the tangent shear modulus to a small value as 0.001 Gi or 0.0001 Gi, and then we continue the analysis, and at any stage to check whether our stress state is within the elastic state or the plastic state, we look at the yield function value. Let's apply this model, the KG model or the bilinear elastic model to performing a triaxial compression test, and this demonstration is suitable for hand calculations, like whatever I am demonstrating is only for hand calculation, so that you can understand the procedure, but the same thing we can apply it in any finite element program, and there are several calculations that we cannot imagine, or we cannot imagine doing that by hand. Okay. Let us take the triaxial compression test performed at a confining pressure sigma 3 of 100 kPa, and let our cohesive strength be 25 and the friction angle is 35 degrees, and our Young's modulus is 35,000, and then the Poisson's ratio is 0.35, and our triaxial compression test is a strain control test. We are applying some strain and then measuring the reaction force through our proving ring. Okay. Let us say that we are applying axial strain in increments of 0.002. It could be anything, like I am just applying this in some reasonable value, so that within short number of cycles we can complete the analysis. Okay. So, our epsilon z, that is in the vertical direction, is 0.002, and at the start of the test all the stresses sigma 1, sigma 3, they are equal, and it is equal at 100. So, if you substitute the sigma 1 and sigma 3 of 100 and then the C and phi in our yield function equation, it is minus 155.67, and obviously the stress state corresponding to the all round pressure state is a dot on the normal stress axis, and it is within the yield limit. So, our F, the yield function value is negative. So, that means that we are in the elastic state, and here in the triaxial compression test we have only two stresses. One is the confining pressure, and that is constant. It's like an axisymmetric case where we have the radial stress sigma 3 and then the vertical stress sigma 1, and we can work in terms of these two stresses that will completely describe the stress state within the triaxial compression test. Now we are applying axial strain increment delta epsilon zz as 0.002, and then the strain increments in the radial direction in the x and y directions are minus mu times delta epsilon z, and our volumetric strain, incremental volumetric strain delta epsilon v is delta epsilon xx plus delta epsilon yy plus delta epsilon zz. Actually, I could have also written it as delta epsilon r. In that case, delta epsilon v is 2 times delta epsilon r plus delta epsilon z. Just to make it a bit more clear, I am using x and y coordinates, but it should be just an odd coordinate, but multiplied with 2. Okay. So, delta epsilon v is 1 minus 2 mu times delta epsilon z, and that is 6 times 10 to the power of minus 4, and if delta epsilon z is compression, delta epsilon v is also compression because it has the same sign. And during the deviated stress application, that is in the second phase, we are applying axial strain, and our confining pressure remains constant. Sigma 3 remains constant at 100. So, that means that our delta sigma xx and delta sigma yy are 0, and our initial bulk modulus is E by 3 times 1 minus 2 nu, that is 38,888.89, and our initial modulus, shear modulus is E by 2 times 1 plus mu, that is 12,962.96, and let us say that the tangent shear modulus after exceeding the yield limit is 0.001 times Gi, that is 12.96, and the constitutive matrix for the triaxial compression test can be written like this: delta sigma xx, delta sigma yy, delta sigma zz, delta sigma xz. Actually, this is you can also take it as delta sigma r, delta sigma theta, and then delta tau, but I am just writing it in terms of x and y for better clarity. And our k plus 4/3 g is the previous step we have calculated both k and g. So, if you calculate k plus 4/3 g is 56,172, k minus 2/3 g is this, and our strain increment is minus 0.35 times 0.002 in both x and y directions, and then delta epsilon z is 0.002, because if you are compressing in the axial direction, there has to be an expansion in the radial direction. So, we have minus, and if you do this, our radial stress increments are coming out as 0, then the axial stress increment is 70, and actually that delta sigma z is just simply E times, that is the Young's modulus is given as 35,000 multiplied by delta epsilon z 0.002, that is 70. That shows that all this calculation whatever we have done is correct. And so, we see that as we are applying the axial compression during the second phase of the test, our confining pressure remains constant. So, now let us do some calculations. So, initially our sigma 1 and sigma 3 are the same 100, and the F is minus 155, and the volume strain is 0, that is the start. And let us increase the axial strain to 0.002, and delta sigma z is 70. So, our sigma 1 is 170. Sigma 1 is the vertical stress, that is sigma z, and our F value is minus 125, and the volumetric strain increment is 6 times 10 to the power of minus 4. And then let us increase the axial strain to 0.004. Once again, since we are in the elastic state, we use our delta sigma z as EI multiplied by delta epsilon z. So, that is 70. So, our sigma 1 is 240, and our yield function is minus 95, and our volumetric strain is 12 times 10 to the power of minus 4. And then we continue, and you see at 0.01 our sigma 1 has reached 450, and our yield function value is minus 6.42, and the volumetric strain is 30 times 10 to the power of minus 4. And since our yield function value is negative, when we apply the next strain increment, we get stress increment of the same thing 70. So, sigma 1 is 520, and now we see that when we calculate the yield function value, it has become positive. This is plus 23.425, which is greater than 0. So, that means that the soil has reached the plastic limit, and now we have to be alert and see what we should do, so that any further increase in the axial strain will not increase the shear stresses. Okay. So, at this stage what we do is we can reset the shear modulus to a small value 0.001 times GI, that is 12.96, and then our tangent Poisson's ratio is 3K minus 2G by 6K plus 2G, that comes to 0.499, and our incremental volumetric strain is 4 times 10 to the power of minus 6. Then increase in the axial stress is 0.07, which is very small compared to the previous value of 70. So, the vertical stress and the volumetric strain changes after the plasticity is see, previously we were here at a strain of 0.012, and our sigma 1 was 520, and our yield function value is 23.425, and our volumetric strain was 36 times 10 to the power of minus 4. And now let us increase the strain to 0.014, that is, we applied a further strain increment of 0.002, and now our delta sigma z increases by only 0.07, because our shear modulus is reduced to a small value of 12.96. Previously it was 12,960, now it is 12.96. So, our delta sigma z is only 0.07. So, our sigma 1 is 520.07, and then our volumetric strain increment now is only 4 times 10 to the power of minus 6. So, this is our volumetric strain, and if you increase the strain by another 0.002, your strain increases to 0.016. So, our sigma 1 is more or less remaining constant at 520, and our volumetric strain is also remaining constant, more or less constant. So, if you plot the stress strain graphs with increasing axial strain, initially your deviator stress will go on increasing, but after the yield limit it remains more or less constant. That is what we have seen here. It is once it has reached 520, it has remained more or less constant. It is only increasing by a small value. and similarly after you reach the plastic limit, your volume has more or less remained constant, because our Poisson's ratio now is very close to 0.5. That shows that the soil is incompressible. And just a note, say as our normal stresses in the triaxial compression test, they are both principal stresses, sigma 1 and sigma 3, so that we can directly apply our Mohr-Coulomb relation. And just for the purpose of hand calculation, that was simple to illustrate that beyond our yield limit, when our yield function value is greater than 0, we set the shear modulus to a small value, and then we see that any further increase in the shear stresses does not happen. Okay. But in a real finite element analysis, it's a very cumbersome process, because we solve first for the displacements, strains, stresses, and then the stresses are the Cartesian stresses sigma xx, sigma yy, and tau xy, and then from these we need to estimate the principal stresses sigma 1 and sigma 3, and then check for the yield limit in terms of our sigma 1 and sigma 3, c and phi. So, actually after reaching the plastic state, the axial stress and the volumetric strain have remained more or less constant. So, that way we should be happy that we are able to simulate some limit on the shear stress. It is not increasing without any bound, and then our volume is remaining constant after the failure. But then in this case, our sigma 1 obtained is 520, while the exact value is 465. There is a huge difference. In fact, our in terms of percentage, it might work out about 20%. And if this happens at a small element level, if you apply it to any bearing capacity problem or something, your bearing capacity estimate could be totally different. Or if you apply it to any slip circle analysis, we will see that our factor of safety is very, very high. Instead of getting 1.3, you might end up getting 1.7, 1.8. That is because of our wrong estimation of our failure stresses. So, how do we increase the accuracy? See, the strain increment is something that we can control. So, instead of applying the strain increment in terms of 0.002, let us say we apply this in 0.001. Your solution accuracy might increase a little bit. That we will see through the Excel program. But then if you reduce the strain increment, the number of computations is going to increase, and your the solution time will be much longer. Okay. So, that also we have to keep in mind. And so, we need a better procedure to obtain more accurate result. Like can we directly estimate our 465 by doing something else? That we will see later. Okay. And the advantage of this bilinear elastic model, it is a very simple model, and we are able to utilize the shear strength parameters c and phi, and then put a limit on the stresses that we generate, and it is able to represent the limit state of the soil. And after reaching the plastic limit, our shear stresses have more or less remained constant, and then we are able to represent the constant volume state after reaching the plastic state. So, that is one of our observations from our laboratory tests. At critical state, our shear stress remains constant, and then volume also remains constant. So, that we are able to simulate by using a simple bilinear elastic model. And all the limit solutions like our bearing capacity or the lateral earth pressures or the factor of safety of the slope on the against the slip circle failure, we can simulate by using the simple bilinear elastic model. But the limitation is the modulus is not a function of time, function of confining pressure. And then not only that, as the stress is increasing, your modulus should go on decreasing. But here we have only bilinear elastic, so our initial modulus remains constant up to shear failure, and then after that once again it remains constant at a very small value. But in our stress strain test, we see that the stress and strain are curvilinear graphs, not straight lines. And another limitation of this bilinear elastic model is we are not able to simulate volume expansion under the shear strains, and the strain hardening and strain softening are also not simulated. We need to go in for better models. And if our strain increment is very large, then we could have very high errors. Say instead of using a strain increment of 0.002, let us say we used 0.1 or 0.005, what would have happened? Okay, that we will see through the Excel program, and our errors could be very large depending on the strain increment that we use. Okay. So, let me just illustrate some applications for the bilinear elastic model, and here is an application for predicting the lateral pressure coefficient under active deformations. So, we have a retaining wall, we have subjected to lateral translation, and we know that our lateral pressures will go on reducing, and on the y axis we have the K, that is the net lateral force divided by 1/2 gamma h square. The net lateral force is, see, we are applying equal horizontal displacement to all the nodes on the retaining wall, and when you apply any displacement, the programs, they calculate a reaction force from our integral B transpose sigma. We calculate a reaction force, and you can sum up all those reaction forces at these nodes, and then that divided by 1/2 gamma h square will give you the K. And so for Young's modulus of 25,000, you need more deformation, whereas with the Young's modulus of 50,000 you need a lesser deformation, and our phi is 40 degrees. So, our K active is about 0.217, which is approximately represented in by both these graphs, and with the modulus of 50,000 we reach the active state faster, and the percentage deformation that you need is about 0.2%, but when your Young's modulus is only 25,000, you need almost 0.4%. And this is with 3 different friction angles: 30 degrees, 40 degrees, 50 degrees, and with 30 degrees your K is 1/3, and when it is 40 degrees it is 0.217, and with 50 degrees it is very small. And you see that with the 30 degrees you need a lesser deformation compared to 50 degrees to reach the active state, and the Young's modulus is the same for all the 3 cases. Just to illustrate what is the effect of friction angle on the lateral earth pressures, this example was worked out. And let us look at the passive state. So, this is on the x axis we have the passive deformation, that is the wall deformations into the soil, and the K0 is 1, and as the wall is pushed into the soil your lateral pressure will go on increasing, and for 30 degrees your Kp is 3, and the lateral pressure coefficient will go on increasing, and at a lateral strain of 2.6%, the soil has reached the plastic limit of Kp of 3, and when friction angle is 35 degrees, it required 3.7%. See, compare this 2.6 and 3.7 to the deformation that you require in the active state. See, for 30 degrees, your required amount of deformation is only about 0.35%. This is for E of 25,000, and for 40 degrees you need about maybe 0.45 or something. But in the case of passive, you require much larger deformations, 2.6 and 3.75, and this is the result with two different K0 values, K0 of 1, K0 of 2. See, when the K0 is higher, you require smaller deformation, because the Kp is 3 and K0 is 2, and so that means that as you are pushing the soil, it can reach faster to reach a K of 3 as compared to reaching a K of 3 from a K0 of 1. So, here this both red and green lines are corresponding to a friction angle of 30 degrees. The Kp is 3. When your initial K0 is 1, you require a deformation of almost 2.6%, but when your K0 is 2, you require only 1.4%. You see the drastic reduction. That is because your initial stress state itself is closer to the passive pressure state, and when friction angle is 35 degrees and K of 1, you require about 3.7% of the wall deformation to reach the passive state. Okay. So, this the bilinear elastic model is a very simple one, and this is one of the first constitutive models that we have worked at, and it is easy to implement because all we are doing is controlling the shear modulus values, and the shear modulus initially is very high, but then after reaching the limit state, the G is set to a small value, so that your further increase of the shear stresses is more or less 0. Okay. So, with this simplistic model, we can predict our bearing capacity solutions or any limit solution like your lateral earth pressures behind the retaining walls, or the slip circle analysis of slopes and prediction of the factor of safety. Okay. So, now let me show you one Excel spreadsheet program, and we can do some interesting calculations. This is a bilinear elastic model in terms of shear modulus and bulk modulus, and our initial the Young's modulus is 35,000 and the Poisson's ratio is 0.35, and this particular one is for simulating the triaxial compression test. And let us take the same values as we have done in the class. Let us take a C of 25, the friction angle of 35 degrees, and the sigma 3 is 100, and the maximum axial stress is 465, and then let us apply axial strain in increments of 0.002, and the reduction factor for the shear modulus is 0.001. So, the tangent shear modulus is 12.963, and then the tangent shear modulus is 0.49. Okay. And our calculations are like this. So, the axial strain of 0.002, the incremental radial strain is minus 0.0007, and then the volumetric strain is 2 times the radial strain plus epsilon z, that is 6 times 10 to the power minus 4, and the increment in the axial stress is 70, and this is our yield function value minus 125. Okay, and our axial stress will go on increasing from 100 to 170, 240, 310, 380, 450, 520. At this stage, we see that our yield function value is positive. So, the further calculations should use our tangent shear modulus instead of the initial shear modulus. So, if that is done, our ds z, that is the axial stress increment, is only 0.07, and our incremental volumetric strain is also very small. Okay, and so you see here our volumetric strain is more or less remaining constant, and our axial stress is remaining very close to 520. So, with increase in the axial strain, it will continue at the same value. Okay. So, now let's see what happens. See, if I apply this in faster increments 0.005, okay, and see our predicted yield stress is 625. See, it is about 625, whereas our maximum stress is 465. So, we see that the accuracy of the solution depends very much on the axial strain increment. Let us now apply this in very small increment 0.001. Okay, and now we see that our predicted stress is 485, which is better than 520, but then our number of load steps has increased. So, that means that we have to spend more time and more computational effort to improvise our solution. So, we can further increase this, let us say 0.0005. Okay. So, our incremental stress is only 17.5, okay, and so our yield stress is 467.5, which is very close to 465, but then the penalty that we are paying is in terms of the number of steps of analysis. So, our stress strain graph is like this, which is so our yield stress is very close to 465, 467, and then the volumetric strain is also very good, like after initial volumetric compression, the volume will remain more or less constant during the critical state in the plastic state. So, at least these two aspects we are able to satisfy, that after failure the shear stress should remain constant, and then after failure your volumetric strains should remain constant. So, the bilinear elastic model is able to represent some aspects of our stress strain relations that we have developed, that beyond the plastic limit the stress will remain constant, and then the volume will remain constant. And since we are applying Mohr-Coulomb relation, we should be able to predict very accurately all the limit bearing capacities or the lateral earth pressures or our factor of safety against slope failure in terms of the slip circle and so on. Okay. So, that is the that's a brief introduction to our bilinear elastic model, and if you have any questions, please send an email to this address profkrg@gmail.com, and then I will respond back to you. So, thank you very much. We will meet next time.